Okay, so thank you all for joining. I think that we can start. So welcome, Martin Mundt. Recent paper, a holistic view of continual learning with deep neural networks, forgotten lessons, and the bridge to active and open world learning. So thank you again, and the stage is yours.
Thank you. So thank you for the invitation, and I'm very happy and pleased to present this together, this work that was authored with my wonderful co-authors who are depicted here. And it's quite nice because I think that all of us come from a slightly non-traditional background with me, for example, having a master's in physics and Julia having a PhD in philosophy. So that I hope this is reflected in the paper. Um, what I'm going to present today is a little bit of a non-traditional paper. So it's not your average 8-page conference paper. But what we actually do is it's more of a position paper. So it's basically in 5 parts, whereas the first one is a survey of what is currently going on in deep continual learning and paradigms that are related. That includes active learning and open set recognition, which we will emphasize. And after that, there is an identification of individual challenges and shortcomings so that we can put forward the position on the necessity of a consolidated view. So the proposal of a natural bridge based on some lessons that have seemed to gone a little bit overlooked. And of course, this would be not as valuable if we didn't have a suggestion of how one could conceive this in neural networks. So we show a practical way to approach this with some empirical validation and some experimental design. And so the main goal of this paper is really to critique in a little bit, in a sense, of what we're doing, and that it's a little bit too narrow. But more than that, rather take what's already been done and build upon it to raise awareness and expand our current practices to ultimately inspire. And just so that we're on a common ground, a quick refresher. What is the predominant view of continual learning? So there's multiple things in the literature called lifelong learning, continuous learning, continual machine learning. Ultimately, it's an evolution, which maybe didn't start with this definition, but it's one of the most prominent early ones that literally just says the system has performed n tasks, and when faced with the n+1th task, it uses the knowledge gained from the n tasks to help the n+1th task. So as you can see, this is rather simple, but puts the idea forward. And of course, over the course of time, people have taken this definition and put in more detail. So one of the, in my opinion, more concise definitions has been put forward in a recent book on lifelong machine learning by Chen and Liu, where in a 2017 initial version, they said it is comprised of 3 main pillars, which is continuous learning. So really the idea of learning over time. While doing that, the accumulation of knowledge and its maintenance in a knowledge base, and of course, the ability to use whatever you encode in knowledge in future learning. Now, recently, I think last or this year, they have also added 2 more pillars, which are the ability to discover new tasks and the ability to learn while working or to learn on the job. I think it would be a great idea if I could have some sound from time to time to make sure that I'm not disconnected. Because I don't see anything, so it's a little bit helpful to just have any form of background noise. Thank you. So what is really missing from this list is, and of course this is non-exhaustive, is we speak about knowledge and retention thereof in a sort of knowledge base, but what does that really mean? And luckily for us, for now, if we constrain ourselves to neural networks, then this is very much based on representations. Although there is a very big open question of how to form these representations, how you can incorporate prior knowledge into this, meaning how do you design the architecture, etc., which is not the objective of this talk. But what is the objective of this talk is essentially the evaluation practice, choosing, ordering, evaluating tasks in the current picture that is predominantly focused on quantifying catastrophic forgetting. So really what we're doing right now, we'll argue, is we're looking at pillars 1 and 2, with occasional analysis of this third pillar of improving a task based on previous knowledge if we actually investigate something like forward transfer or backward transfer. But we're really missing things beyond that. So in order to explain that a little bit better, what are we currently doing? And what we notice is that the devil is actually really in the details about evaluation, because there's a lot of paradigms that are strongly related. So you could take, this is a snapshot from the paper, and you can find the very rigorous definition in the paper as well. But in summary, for example, you have transfer learning, which is very related because you say something like you leverage the source task representations to accelerate learning and to improve a new task. So the difference to what people would call continual learning would be that this is very much unidirectional, meaning you only care about whatever task you transfer to. You don't really necessarily care about where you're coming from. And similarly, you have other tasks such as multitask learning, where you just form a joint hypothesis based over multiple tasks, but like all at the same time. Or you do online learning, where the emphasis is more on the online adaptation if you have real-time requirements, and maybe doing greedy updating steps. Maybe few-shot learning or zero-shot learning, where the question is more about the small data regime. And so there's a lot of work in the literature, and this is strongly related. But what people typically do right now in deep continual learning is they are very inspired from benchmarks and learning on benchmarks in isolation and comparing what has been done. So this is a very small example, which is rather independent of whether you approach this from a supervised or unsupervised perspective of generative modeling, for example. You can take a first task, which could be the first two tasks, the first two digits of MNIST or some images from a natural data set like ImageNet, and then you start training on those. And then later you introduce something else, like the second and third digit or other animals, and you train exclusively on that. And while you're doing that, in this training process, you attempt to protect the knowledge that you have in your knowledge base from previous tasks while being able to encode new tasks to your advantage. So you essentially do this over multiple tasks, and then you start running some baseline algorithms, which means you start training in isolation, essentially on all tasks at once, and use other lifelong or continual learning machine learning approaches and just compare them. And when you compare them, usually you try to boil this down to as simple as possible metrics, such as accuracy or some negative log likelihood. Now, of course, you might say, wow, this is a little bit shallow. That's not actually what people are doing. People are going a little bit beyond that. And that's actually correct. So people have put forward many discussions and reviews in which they argue about the necessity of also taking a look at how much information can you transfer forward? How much does it help you? How much can you retrospectively improve when you go along this route? What's your memory and computation trade-off of individual methods? Is there necessity for maybe task boundaries to be explicitly encoded? Do you need a prediction oracle for these task boundaries? All these sorts of questions. And it's really great work, and we really appreciate these works. But what we think is really missing is moving outside of these closed wall benchmarks. So there is at least three popular, maybe not so popular, but well-known paradigms that are typically currently undervalued in our view, which is curriculum learning. So the question about how can you order your data such that you can actually train in a more efficient way that is related to an inherent difficulty of individual data instances. So if you just evaluate this as it's done right now in the literature, you would essentially just do it the same way. You would just take a benchmark data set and you would see how you can rearrange it such that you get a better curve. But what you need in addition is actually what people refer to as open world learning. And this is the ability for your model at any point in time to actually identify and recognize unseen data belonging to unknown tasks, such that you can avoid to do a misprediction, but also to set them aside and include them for later learning. So this is something that is currently not evaluated at all, and because we're just fixed on benchmarks. And the third thing, which is very prominent in the literature, but usually less so associated with continual learning right now, is active learning, which is literally just the question of how can you include data step by step to get the best performance gain. And again, unfortunately, active learning in itself is very much evaluated in this benchmark sort of scenario. So why is that? I mean, of course, these questions are really challenging, especially the curriculum and open world questions. But if we take a moment to think about it, then continual learning should really be encompassing all of these paradigms. It should really be possible to include online steps. It should be possible to be in the open world, to recognize things that you don't know. You should be able to query instances. And this is why we've taken to writing this paper, because we wanted to highlight certain limitations, but also show that there's a lot of synergy. And if we go towards a common view, then we can benefit from this quite a lot. So before going on into details, let's just make sure that everyone knows what active learning and open set recognition is. So active learning in our proposition is really the antagonist to catastrophic forgetting. It's like the reverse side of the same coin. So when you look at continual learning and you train on one task and then on the next task, what you really want to do is you want to avoid catastrophic inference, which is having your parameters being overwritten such that they only encode your second task and everything about the first task is forgotten. So you want to really protect and minimize the performance loss. But in active learning, you do the reverse thing. You also have multiple things sequentially, multiple sequential data, but you want to choose your next data such that you actually get the best gain in performance. So it's quite similar, except for it's flipped from the other side. So people in active learning, usually they take a labeled data set, then they train on it, get a model, then they start querying from either a pool or a data stream. This is usually unlabeled, so that if it's supervised, a human or some other oracle can annotate this and you kind of just keep repeating this loop, which inherently then actually incorporates the question of what's good ordering and what is the significance of training in a good order. On the other hand, we've been talking about closed world benchmarks for a couple of slides now. What does that actually mean? That means that there's a certain type of data that we can encounter once we move our model outside of a benchmark. And this is obviously the first thing, the knowns, which is any data sample that is basically related to what the distribution which you've seen during training. So you essentially just assume your model prediction is accurate and confident. And just as there's knowns, there's also things that are called known unknowns, which is unknown instances that your model cannot predict confidently, but through some sort of a little bit of prior knowledge, maybe by including some negative examples or some methods to assess uncertainty, you can still get your model to produce something where you know that this is not seen. Now, the problem that's frequently overlooked is that there's a third set of data, which is called unknown unknowns. And this has been known for quite a while, that there's a lot of unseen instances belonging to unexplored and unknown data distributions for which predictions with neural networks, independently of whether they're discriminative or generative, are typically very overconfident but false. And so this is a long-standing problem. And this is something that we believe is very important when you move a model into practice. So what we've done is we've started with a survey and a traditional taxonomy of how people usually approach these things right now. And on the left side, you can see that there's this big bubble called deep continual learning, which can be categorized traditionally into these regularization approaches that protect parameters explicitly. There's replay approaches that just rehearse some data or generate some data for rehearsal. There's architectural approaches that modify the architecture to protect certain paths. And of course, there's anything combined. And of course, in this presentation, this is the part I'm basically skipping because it's quite a long section in the paper. And I think it's enough to know the taxonomy here and not each and every individual work, but I highly encourage you to look into the paper if you want to get a more detailed overview. Now, in open set recognition and active learning, you have quite a similar picture. On the one hand, you can say that, okay, naively, I can tackle open set recognition by just using some sort of predictive anomaly, meaning I assume that my model actually does put out an uncertainty or some confidence that can separate unknown unknowns from other data, even though multiple people in the literature have claimed that have claimed otherwise. And so essentially, there still is a lot of work that is doing that, or using prior knowledge to say, yeah, we can just, we know what we don't know, so let's just put it in. But a third path is meta recognition, which is saying, I don't want to put any explicit assumption of what I don't know into there. I just want to do meta recognition on top of what I already have. And so this is what we'll include in this thread to join deep continual learning, open set recognition, and active learning together. Because active learning has quite a similar problematic that people use uncertainty heuristics to think that you can just query new data without taking into account that you can just query things that are basically noise or unrepresentative, which don't protect you from these unknown unknowns. So in the end, we want to get into the middle and connect these three paradigms together and show that there's a lot to gain when doing so. So to understand that a little bit better, that these three things are actually interdependent in every possible direction. So active learning, continual learning are related, OpenSet is related to it, and all the ways, we formulated 5 basically accumulated insights that people have postulated in past literature that we have unfortunately observed to be a little bit overlooked in the current era of modern deep learning, which of course is again related to these questions being genuinely difficult. However, we also believe that taking a look at these lessons is very valuable, and we actually need them. They're very imperative to assessing our progress and moving the field forward. So let's just dive into these 5 lessons because they're quite intuitive to understand. And again, if you want more detailed information, please take a look at the paper. So the first one is the one that is mainly overlooked the most, which is machine learning models are by definition trained in a closed world because you have a benchmark, you have a limited amount of data. And as soon as you're done training and you start deploying this beyond the benchmark evaluation into some real world application, then this real world is typically not confined. And you are encountering a lot of data that you have not seen during training, for which you cannot guarantee that your network is going to produce something that's not overconfident and false. So this is an illustration from one of our previous papers where literally if you train a network on fashion items and you put an image in of an owl, you will get that this is a t-shirt with 95% confidence. So the person who is interested in this field might now argue, okay, uncertainty to the rescue. I mean, we know there's uncertainty techniques that have now trickled into deep learning that allow you to assess uncertainty in deep learning. So let's just use those. And the problem is this is not really predictive either. And this is particularly interesting for active learning because in active learning, you're essentially querying from an open world and hoping that what you query is meaningful. So uncertainty does not protect you. And to give you a little bit of a quantitative examples to give you the intuition, I have 2 plots here on the left and the right side, also from one of our previous papers, which shows a network that is trained on fashion MNIST and then evaluated on a variety of data sets such as MNIST, KMNIST, SciFar, even an audio data set. And on the left, you see what just the accumulated classification confidence and classification entropy, predictive entropy is when you just accumulate the entire data set. You can see it's essentially indistinguishable, which is very worrisome because this means that an audio example will be categorized with 99% confidence as a fashion item. And now when you do the same thing with a technique called Monte Carlo dropout, which just allows you to sample your model with dropout at every layer to emulate a Bernoulli weight distribution, then you can see that, well, okay, this helps a little bit, but there's a really big chunk of maybe like 50% that's still overlapping. So of course, this helps you in a sense, but it doesn't solve the problem. So you're still going to get a lot of data that you'll falsely attribute to something that it's really not. Now, the third thing that you might want to say is, okay, cool. So I can't really use uncertainty and other predictive heuristics. So I am just going to calibrate it. I am going to use whatever explicit knowledge I have of examples that I think I might encounter in the future and include them explicitly to calibrate my uncertainty or adapt my loss. Of course, if you look at the left picture taken from a recent nice review on this topic, you have four stars representing your classes and some dots and a decision boundary. This might be very nice, and you might be able to do that for this scenario. But in reality, of course, your closed set that your data set defines is very, very small in comparison to the basically infinite high-dimensional open space. So as soon as you zoom out of this picture, you're going to have to ask yourself the question, can I really include everything that I can potentially ever encounter in the real world, which is really just bound by the universe? And well, the obvious answer, as we argue and as this paper has argued before, is no, you cannot. Lessons 4 and 5 are a little bit on a different side, which is data and task ordering. Data and task ordering is really essential. And it's quite interesting for us to see that this is something that is basically the core of active learning, but is something that in continual learning is very much not evaluated. And I will come to this in a couple of slides with more specific examples. But here's an example from a curriculum learning paper from 2009 that just shows that just by rearranging the data in a certain curriculum, which here means they have imposed a sort of difficulty ranking on very primitive shapes. And when you then train, you can surpass whatever you have done if you just sample data at random into your training. And the fifth lesson is perhaps the one that is most difficult to analyze, because it is telling you that parameter and architecture growth are not distinct methods to address some particular challenge, such as catastrophic forgetting. They're really at the core of everything we do in machine learning. And the reason why we formulated this lesson, even though this lesson might be apparent to a lot of people in the community, is because there's an increasing amount of papers in continual learning that advocate architectural methods as a unique sort of branch to tackle continual learning. And what is shown here is from another paper, from an active learning paper that has done this with neural architecture search, where you can see 3 different query metrics based on just a softmax response, based on just Monte Carlo dropout-based uncertainty in the prediction or the construction of a course set. And you see 3 curves. In the blue, you see a fixed resonant architecture. In the red, you see a fixed architecture, but a small one. And in the black, you see a nice growing architecture. And the problem with that is the blue and the red curve, they essentially have different performance or are supersede one another at different points in amount of data. And this is obviously very known in deep learning that shallow models usually perform a lot better when there's scarce data available, and deep nets only really surpasses when you get a lot of data. So a model that is growing continually as your amount of data or your data complexity grows is quite natural to have. Now, the challenge, of course, arises when you say that this is a method to address catastrophic forgetting and continual learning, or maybe even active learning, because you can literally do this for anything and you will get the same example. You can do this for future learning, etc., because you're just gaining performance because your architecture is more adapted to the data that you have at this current point in time. So the danger then becomes comparing this to other methods that are non-architectural in that sense, because it's kind of an apples to pears comparison, because you could plug this in everywhere and gain this benefit. So we're not really saying that this is a bad thing to do. In fact, we're actually saying this is necessary everywhere. We're just saying that this is not really something that should be advocated as treating a particular problem. So this is 5 lessons. Now the question is, how do these come together and why do these belong together? So what we postulate in paper is we say that open set recognition is really the natural interface to bring these things together, especially bridging active learning and continual learning, while being able to reject things that are unknown. So if you take a look at the very left illustration, then you see some 2-dimensional space, some embedding, and you maybe have 3 classes with the star denoting the mean. What you really want to do is you want to form some sort of red circle around the area where you have high density and avoid anything that's outside of that, even if that includes some inherently present outliers. And we find, or previously people have found, that you can do this by using extreme value theory. So essentially what you do is you accumulate your data and you fit some distribution that captures your tail. So you get something like the blue curve with the distribution, where you have something like the distance to the class mean on the x-axis and the number of data points on the y-axis, and you see that this forms a distribution which can generally be characterized through some long tail distribution. And once you have this distribution parameterized, you could obviously always use the cumulative distribution function to get a sense of how far is a data point away from what I've seen frequently. So really this distribution, if you get a grip on this, and we'll see how to do this exactly in a couple of slides for neural networks, what you can do is you can use this to do all of these things basically with one mechanism. So starting with, if you want to recognize something that is unknown, or actually truly unknown, and for which you want to avert an untrustworthy predictions, you can take a look at your outlier probability in terms of distance to your high density areas. And as soon as this is outside of your red circle, essentially, and has an outlier probability of 1, you can quite confidently say, I don't know if my model is actually going to do the correct prediction. It might or it might not. But what I do know is this is something that I have not seen in my training data distribution, so I should not trust it. And now you can use the same thing for active learning, because essentially that means If you want to say, I don't trust it, then this could be anything. This could be noise, this could be uninformative, so you want to avoid this. But on the other hand, you also want to avoid anything that is very close to what you've observed, like a really high dense area, because it's very likely that if you query there, you're going to get something that's highly redundant. So you can use the same curve and just query basically data that is in the middle, so that has some outlier probability, but it's really close to your red circle, so that you expand your space like step by step and only move out of your comfort zone just ever so slightly. Now, what about continual learning? You can do the inverse. If you have a curve that's telling you where your high density area is and how it decays when you move away from it, you can essentially just inversely sample this. You can say, just draw from this distribution, get points in my embedded space, and then use this to rehearse, or at least a subset of it. So basically discretize this curve and take some amount of samples from this bin. So, okay, this was really conceptual. I hope that the idea is maybe just a little bit clear, but let's dive into detail of how we can do this in a neural network so that it becomes clear. So the first thing we argue is we should use something like a variational autoencoder. And now everything that I'm going to show now is essentially a proposition of one way of how you can implement this. It's not the only way for sure. But what we said in previous papers is use an autoencoder for this, because this has one certain advantage. You get an approximation of your data distribution in your latent space, which is good, even though it might not be perfect, and you get generative factors for your data distribution. So essentially, you no longer need to rely on some output heuristic like a classifier confidence or a negative likelihood, for which you know that it's overconfident, but you can start basing your decision on something that is actually explicitly related to your data distribution. So what we usually do, for example, if we want to train this for a supervised problem, you can just say, okay, just put a linear classification term on your latent space such that it has some sort of disentangled space for classes. And what you do then is you use a beta VAE, because you can control the amount of disentanglement that you get in this latent space. So here's an example for, I think, Fashion MNIST with a two-dimensional latent space, just to illustrate this. If you have a very large beta on your KL divergence term, then this means you're very much pushing whatever approximate posterior you encode into your prior, which in this is a unit Gaussian. And the more you do this, the more you collapse the inherent data structure into this prior. So for a while, people have believed that this is something that you do want to do in variational autoencoders, but distinct works have actually argued that you're losing your data structure when you do that, and this is not something that you want to do. So they have coined something that is referred to as the aggregate posterior, which literally just describes the actual encoding that you get. And when your beta is small enough, but not too small, you can see on the very right side that you can get a disentanglement of the individual classes in this case, while still remaining in your region of the prior, essentially. But of course, you get some holes in between that are desired such that you can classify. But they're a problem if you want to, or you need to identify them if you want to predict unknowns, or if you want to sample from it, etc. So what do you do explicitly to get this distribution I've talked about earlier? It's actually quite simple. You literally just accumulate all your mean latent values. So you just get your Z, and then you just calculate for your entire training set, and then you just calculate the distance of every individual element in your training set to this mean. So you just form a set. And this set forms the basis for your distribution fit, which again is usually something that is long tail distributed, like a Weibull distribution, which essentially is a skewed Gaussian with a very long tail. So it's a 3-parameter distribution. Now, when you have that, the first thing, as we said, is we can use this cumulative distribution function to determine when an instance is lying outside of this out of this boundary. So here's on the left, there's an illustration where you see the same latent space, but now in addition to these fashion MNIST data points, you now also see what happens when you put in Cypher10 and RDO MNIST. So you can see, unfortunately, they fall exactly into the prior. Actually, they fall at the center, which is very good if you think of the KL divergence, because this is a unit Gaussian after all. But at the same time, it's very far away from whatever you've seen in your aggregate posterior. So if you look on the right side and you take something like your predictive entropy, if you're trying to classify on this, then you see the dataset predictive entropy for multiple datasets on the x-axis, and the percentage of the dataset being an outlier, if you were to threshold it at that point, And you can see that there's no point in this diagram that you can make a confident decision that separates everything that you haven't seen from what you have seen. But as soon as you do this based on the distance in this latent space, on the bottom one, you can see that actually at any point in time, you are able to just distinguish which is what you want. So using such a method, you can encode a new example and immediately predict, even if it matches your prior, that this is something that does not belong to the data distribution that you have observed during training. So you can set this aside, or you can use this for querying, such as for active learning, for example, where you basically now start to query in batches, in mini batches, everything that has an outlier probability that is a little bit higher than what you've seen, but not too high, so that you assume that it's some noise or something unmeaningful. And of course, we've evaluated this with ResNets on some popular data sets, really easy data sets, actually, MNIST and CIFAR. We just start with a couple of data instances and then add mini batches of 100. And well, not surprisingly, I think our method outperforms the traditional heuristics such as Monte Carlo-based predictive entropy, or even just reconstruction loss or a random sampling. Because in contrast to these heuristics, this method is essentially based on your distribution and queries whatever is just ever so slightly outlying of your distribution. So it has a semantic meaning. So this is the individual benefit that you get when you use this open world sort of aware concept in active learning. I'm going to show you the same thing on the next slide for continual learning, but much more importantly, after that, I'm going to show you why it's very imperative beyond just moving this benchmark table by a couple of percent. I think I've dinged. I don't know if I should. I don't think I can go out of this presentation. I'm sorry.
Yeah, there's a message you can, a question you can answer later on.
Okay, I think there's just a couple of slides, and then we can just delve into questions and discuss. Now, except for continual learning, you can do the opposite. When you have this distribution, you can essentially reverse sample this. So you just sample from this distribution, you get a latent space value. And this latent space value you can do two things with. One, you can use it for exemplar rehearsal by simply checking whatever latent value you have received, which image does it correspond to, which image lies closest to it, and take that image to use as an exemplar. Or if you say, I don't want to store exemplars in memory because I am very memory aware, I want to use generative rehearsal because I've trained a generative model, I can use the Z value that matches my data distribution, my aggregate posterior, and sample a data point, generate a data point, while at the same time avoiding any samples that come from a low density area. Now, the first thing to say about that for exemplars is exemplar retention and evaluation thereof is actually very challenging. So the first thing we wanted to do is we wanted to show this traditional curve of, okay, here's a couple of tasks in a row, MNIST and CIFAR 10 in a single head. So you just encode this all into the same network, and you monitor your accuracy over time to assess catastrophic forgetting. And what we see is that what really matters the most is not so much the precise method you use to extract your exemplars, but what matters the most is the way that you sample during your training. So there's a big open question of, do you concatenate the core set that you've extracted with the new task? Do you shuffle it at random? Do you maybe oversample the core set, or do you balance the classes? So there's three things we've done just to check this. Is we've said we do unbalanced, so meaning whatever amount of exemplars we extract, we just concatenate the new data with it and keep on training. We see this performs the worst, obviously, because our exemplars are constitute much less examples than the new task. We have seen that we can balance this by just saying, okay, take as many exemplars as you take new task data in each mini batch. But then, of course, the more tasks you accumulate, this is still imbalanced because your core set will contain more and more classes or concepts, but your new task always arrives just with one or two concepts. So we can also say that, okay, we oversample the exemplars even more and just take as much of the exemplars as is percentually described in terms of classes and concepts. So the message here is really just, if you change this sampling procedure, you get like 5 to 6 to 10% performance differences, which is really troubling if you want to analyze a particular exemplar rehearsal method. So what we said is, okay, let's not do that. Let's instead do this thing. Let's take the exemplars that we extract and just start training from scratch on them to assess how good the approximation of this exemplar set is with respect to the entire data distribution. So we've done that for these two data sets for different sizes. And one of the challenges here, of course, is that many papers in the literature only evaluate exemplar sizes, core set sizes that are very large. So there's no perceivable difference. But as soon as you start moving towards smaller amounts of exemplars that are retained, you start seeing massive differences with respect to approaches like ours that are based on some sort of explicit representation of the distribution versus things that are just heuristic or random. So you can see this by just observing the variance, for example, in random sampling, if you only store a couple of examples, which is quite intuitive, right? But what this should really tell you is your exemplar extraction mechanism should be based on your distribution so that you make sure that you resemble you subsample essentially your distribution. Now, this is an illustration of what that actually means, because, for example, on the left side, you have a greedy approach that just gets k centers, k exemplars to store by just maximizing the distances such as to span the entire space. But of course, spanning the entire space is not synonymous with actually approximating the distribution. So you can see on the left side, if you plot the black crosses and compare them with the actual colored distributions, then you can see that there's a lot of deviation in contrast to this extreme value theory approach on the right. So this is the intuition of why the right one works better. For the generative part, just to give you an illustration from one of our other papers, is why this matters is because when you sample from low density areas, you essentially, again, have no guarantee that whatever you generate is of good quality. So here's an array of images from a flower dataset using an introspection VAE, where you can see the image that is generated and the score above that is purely based on the value of Z that you sample and its outlier likelihood. And you can see that just by taking a look at the value of Z and getting an outlier value of like 1.31, you can essentially predict that this is going to be a good quality example that is representative of my data set. And as soon as you move outside of this, well, I mean, it's going to generate something, but maybe this is more of artistic value than it is of data set rehearsal value. Now, why is this important that we use this beyond just improving each and every individual method? And now this comes to what happens when we move this to the open world. So meaning, what if we encounter data that is beyond our benchmark? And one of the simplest things you can do that isn't even about whether you're going to encounter a fish if you've trained a fashion classifier is, what if you encounter any data that is corrupt or perturbed or just outlying in any other form? And there's been a recent study from last year by Hendricks and Dietrich that have shown that if you include just very basic camera corruptions such as blur and noise or maybe pixelation, any deep neural network degrades massively. And where so, any deep neural network degrades equally massively, meaning a ResNet is no better than an AlexNet in terms of robustness towards these examples. So what we've done is we've included a very small portion of these examples in training, because we essentially say that, okay, if we say that we query by uncertainty in active learning, for example, then this is something that we believe will be queried because it's very different from our data set, but it's outlying so much that it's unmeaningful. And this is exactly what we want to prevent with our methods, where we sample essentially still reasonably close to the data set. So we've basically constructed the same accuracy tables and same plots that we've seen before with a minor portion of corrupted data that is still more than the amount of queries we do to check this hypothesis. And what we find is very similar to what these people have found, is that every method degrades except for ours and random sampling. Random sampling doesn't degrade naturally because random sampling doesn't really care if there's just a couple of minor perturbations, because it's just not enough in terms of absolute amount. And ours doesn't care because we just explicitly do not sample regions that are very much outside. But every other method degrades to a point where it's actually now performing worse than random sampling. So the question is, while we're making progress, are we really, are we making this progress in the real world as well, or are we just making progress on our benchmark? So I hope that this has convinced you at least that active learning, open set recognition, and continual learning, they're related. And that you must regard the open world for sure. And now on the last experiment, I'm going to show you why active learning and continual learning are also related, because you can essentially ask the question of what data should you query next when you want to build a curriculum continual learning that outperforms just random sampling. So what we've done is we've investigated training on data sets and monitoring catastrophic forgetting on some data sets with 4 different orderings, where the one is something that everyone does is you just train in sequence of the class ID. The second one is you randomize the order and see what happens. And then we propose 2 curricula. One is using the open set method, you query whatever class or concept next that is the largest outlying, or you build the anti-curriculum and query whatever task next that is most resembling to what you've previously learned. So you can just do this with the same equation and just take the max. And on the left hand, we have a plot where you can see runs averaged over 5 experimental repetitions and their statistical deviations on Cypher 100, just with the real data in the upper bound, meaning you do not actually use any continual learning mechanism to prevent catastrophic forgetting. You literally just accumulate the real data in an upper bound step by step and just grow the data set. And what you can see is, well, if you do this 5 times random, then this performs very similar to your sequential class ID. But when you do outlying first or closest first, you get very, very major gaps at any point in time. Major gaps that we argue are actually much, much more major than the incremental gains that we usually get from each and every individual method that we propose. Now, of course, you could always, on the right side, we show the same thing for generative rehearsal, just to show that this is something that is not exclusive to this particular experiment for audio data. So there's a different modality and also a different mechanism to rehearse. You essentially see the same pattern, that you really want to make sure your data is ordered in a meaningful way. When you take a look at the images for Cypher, this means, for example, that when you have trained on a whale and a shark, then you do not want to query some other fish as the next thing, but you want to query something that's very distinct, maybe a coral or some other form of animal. Now you could always say, okay, yeah, why does this matter? Why should I care about this? This is like the next step. Unfortunately, really isn't, because randomization of task orders is something that's very prominent in the literature. And our worry is a little bit that if you have one paper that says we randomize task order, here's our result, and they don't do this enough many times to get statistical significance, you might or might not have a good shot. Or when you say you take a subset of ImageNet because the entire data set is too large, which is also typically done, you might or might not take the 20 classes that are very easy or very hard to get to train, right? So even if we don't actually care about this full curve, we should care about it in our data set, in our experimental design, because we want to make sure that our experiments are comparable. So, okay, this has been quite a ride. I hope I could at least portray the essence of the paper in a couple of slides. The paper is really long, so I strongly encourage you to read it if you want to get all the details. But I just want to conclude on a little bit of an outlook. So what we've done at the end of the paper is we want to propose maybe an updated version of the continual machine learning definition. And essentially, without reading all of this, the parts that are new is the sentence, at any point in time, the learner must be able to robustly identify unseen unknown data instances and rank order them according to similarity with existing tasks in order to actively build a learning curriculum. So we think this is really essential if we want to move this forward and move our continual learning evaluation practices beyond the benchmarking of well-known stuff. Now, what does that mean if we want to evaluate the system? This means that we really want to get a bigger loop. So in addition to the neural network model that we have in the center, we would now require a neural network model that has some sort of open set recognition capability, such that when you evaluate what you see in the bottom, you can actually identify the overlap with the existing knowledge in some rigorous fashion. And in addition to your regular output prediction, you also get some sort of statistical measure of novelty. Because once you have this, you can base any decision based on this. You can base your decision of what to query next on it, or you can even go as far as saying, okay, if I encounter data in my stream that's really not statistically deviating from what I've seen all the time, I don't even need to protect my model from catastrophic forgetting. I can just fine tune it because it's essentially the same thing anyway. Or vice versa, if I see something that's very, very, very distinct, I can now switch my flip and say, okay, let's do some rehearsal, let's do some regularization, etc. So what you should really take away from this is, or I hope I could inspire you to take away, that our current definition and practices are really nice, and we're making progress in the sense of that we're proposing really intricate algorithms. But the evaluation and the way we see it right now, in our view, is a little bit too narrow, particularly when you observe that closed world benchmarking is not necessarily indicative of progress in real world applications. So separate, instead of treating these paradigms separately, like we've been used to for the last couple of decades, we should really move towards a more systematic, system-wide study that doesn't just examine these key aspects and contributions in isolation, but also pays attention to the whole. So we essentially need to do both, because you need to examine the key aspects and contributions in isolation to make sure it's better than something else. But you still need to also evaluate this on a whole to make sure that you're making progress in general and not just improving on some arbitrarily conceived, contrived benchmark. So in a sense, these things are all part of the same puzzle that we should challenge. And we hope that we've proposed a common framework that gives at least one example of how this could be attempted to encourage other peoples to suggest alternative approaches and move towards a better evaluation. With that, I thank you for your attention, and I hope you've enjoyed it, and I'm open to any questions, and also feel free to email me with any further input.
Oh, thank you so much, Martin, for your great talk. I really enjoyed it, especially the nice infographics that you put there, and as well as the very well made literature review, putting together these three different fields. So I really enjoyed that, and I will use your work for sure to refer to all these different approaches and how they can blend together. So maybe I can start with just a question for you, and then we can let the others talk as well.
Sure.
So one thing that you're pushing here is essentially to expand, I would say, the focus of continual learning also to encapsulate or at least address these two different worlds, active learning and open set learning. But my question is, do you think that this is a priority for continual learning, or should we rather address the idea to encapsulate low supervision methods and approaches and settings? So trying to go from these very supervised learning setting of continual learning that we are used to towards like more self-supervision, unsupervised learning. I mean, I agree that open set learning and active learning are especially useful for real-world applications, and it's kind of pointless to work on supervised continual learning as we're doing today if the target is like real world applications. But at the same time, I find that there is a value in trying to lower the amount of supervision for the very nature of continual learning.
Oh,
And
absolutely.
yeah. So I wanted to know what you think about I mean, these and why did you choose, these priorities and this idea to merge these fields together instead of in that other direction? Yeah.
So this is an excellent question, actually, and I think the choice of what has been presented is less about that. I think that supervised learning is the way to go, but more of this is a really good example to illustrate what we need to move beyond right now. And in fact, if you've observed the arguments such that you should use a VAE because you can approximate your data distribution and then you can base your decisions based on the data distribution, this is essentially moving towards unsupervision.
Right.
And I agree, but still in unsupervised learning, you have the exact same challenge. So this doesn't go away. And I'm just when I first seen this paper on this robustness concern and other open world concerns that you could just basically feed in anything arbitrary into your network and it just dramatically fails. This has really pushed the trigger for me that for all of the machine learning we do, we need to make sure that whatever we produce in 10 years isn't just exclusive towards, okay, I've improved the ImageNet benchmark, but it's actually something that we can transfer to other things and transfer to real worlds. And of course, when we do that, other agendas such as reducing the amount of supervision, the amount of samples that we need are actually equally important. But I think they're part of the same puzzle.
Totally. Thank you so much. Do you have any other question for Martin?
Hi, can you hear me?
Yes, we can.
Okay. Hi, thanks Martin for the nice talk. I have a question regarding the open set recognition.
Yes.
Like, how do you ensure that, let's say you get some out of distribution sample, how do you ensure that it's still not projected into an area of the feature space that you've already seen? Like, let's say you have some area that's reserved for some classes. How do you make sure that new data doesn't get projected to this one?
Mm-hmm.
Do you have,
so there's a short answer and a long answer to this one. The long answer, essentially, you should take a look at, where do I have it? I referenced it on one of the slides. Much before that. So the long answer, if you take a look at this paper, what we evaluate there is we evaluate the differences between purely discriminative and discriminative plus generative approaches. Because the thing about purely discriminative approaches, I would say, is you don't protect this, because you can always have a classifier that has some sort of embedding that, like you said, projects a new instance to the exact same space. Because maybe if you have, let's say you have airplanes and you have cars, then the easiest feature you can learn to separate these two is just saying that the sky is blue. And of course, now if you feed in an image of a ship, then this is blue. It's an airplane, right? It's going to get projected to the same point. So what we have shown on this quantitatively in this paper is that, of course, when you move to a generative approach, even if you include a classification objective in the generative approach, you are still concerned with encoding your data distribution and replicating it. And that means that you can encode other features than just saying sky's blue, because you need to encode actually everything that is statistically present in your data set. And so, of course, this doesn't protect anything from still being projected to a similar point in latent space. Maybe there still is like an adversarial example that could get projected here. But my argument would be, for the majority of the more obvious cases, this will protect it from being projected to the same point.
Okay, yeah. So you basically, the generative part is the main protector in this case.
Yeah. So even if you're purely interested in classification, you would still want to train basically a generative model, even if you don't want to generate data with a decoder or something. And essentially, this doesn't even need to be a VAE. I mean, you could use some other technique.
Okay. Yeah, makes sense. Thanks.
Thank you.
Then also, Martin, we have another question in the chat.
Oh, we do. Okay, how can we guarantee the representational space discovered by a VAE or other generative models is useful for the supervised learning task? So you guarantee this in the sense that you guarantee anything in optimization. You can add the objective to it. So for example, in this one, when you see this diagram, then pretty much the green and the blue part correspond to a conventional VAE, but you can always add a linear classification objective on your latent space. So just put the log likelihood of this value of Z belonging to a particular class explicitly on there. So of course you cannot guarantee this because optimization can always fail, but of course your data distribution approximation can fail in a VAE as well, etc. So there's the trouble of anything that's numerically optimized. But at least you can say that if this thing learns how to successfully classify, then this Z value has to be partitioned in a way that the classes are distinct because it's linear. So there needs to be a linear separation available. So, and if you have a linear separation in a space, in a latent space, then it's useful for your supervised objective. I hope that answers your question, but if not, you could you can.
Yeah, thank you very much for answering my question. Yeah.
Okay, great.
Cool. Any other question?
So I'd like to hear your opinion about the relation between continual learning and a new trend of object-oriented learning. It feels like these two directions there should be some intrinsic relation, but I haven't seen people talking too much about it.
Yeah, I think so maybe, I mean, if we want to have a nuanced discussion about the relations, maybe we can take this offline. For the online answer about my opinion is that while writing this paper, I mean, this took multiple months, we found that there's actually a lot of different paradigms that are extremely closely related, but rarely talked about in conjunction. And this is partially maybe due to the nature of our current publication process, where we sort of push these 8-page papers into a conference, and then because of space limits, it's naturally confined to just basically push in one direction, right? So there's not much room to talk about interrelations and transcending paradigms. So in that sense, like I said in the beginning, I think many of these things, even future learning, etc., they are all related on a big scale. And I hope that we can maybe find some way to, in addition to having the conference papers, also pushing forward more work that extends in a different fashion.
Thanks.
Any more questions? Anything else? A comment or final thank to Martin? Okay, so thank you again, Martin, for your time and your great talk. I'll see you guys for the next reading group session next Friday then. Thank you again for joining and see you soon. Bye.
Thank you for the invitation. Bye.
You're welcome.